And so to diagram this cell, we have two beakers. In these beakers, we have strips of metal. We have zinc 0 as one of the metal strips, and copper 0 as the other metal strip. These metal strips are immersed in solutions. These solutions contain the positive ions of our metals with a spectator ion. In this case, zinc sulfate, and in this case, copper 2 sulfate. This provides a source of zinc ions. This provides a source of copper ions. We connect the metal strips with wires to a device that's going to be powered by the electricity passing through the wires, our load. This load can be a voltmeter, or it can be anything that's powered by electricity. The camcorder that I am recording this on right now is the load, because it's using the electricity that the battery is providing. And to connect the two solutions, to connect the internal circuit, we put a salt bridge that contains a salt that does not contain either zinc or copper. Because zinc is listed higher than copper on reference table J, the zinc is going to undergo oxidation, and the copper plus 2 is going to undergo reduction. So what happens is the zinc 0 undergoes oxidation. Zinc 0 turns into zinc plus 2 by losing 2 electrons. The 2 electrons go through the wire and power the device that we call a load. In the meantime, the zinc strip dissolves and the zinc plus 2 goes into solution. Every zinc that leaves makes the zinc strip that much smaller. When the zinc plus 2 goes into solution, if we're using sodium chloride as our salt bridge, Na being positive, chloride being negative, the negative chloride ions go through the salt bridge in this direction to help cancel out the zinc. After the load is finished using the electrons get pulled through the wire into the copper strip. But of course, it's not copper 0 that's gaining electrons. Metals can't gain electrons. Only metal ions can. So the electrons coat the strip. The copper plus 2 ions are attracted to those electrons. And as soon as they touch the metal strip, they pick up those electrons and turn into solid copper. So as soon as they touch the strip, the copper strip gets a little bit larger. Because the positive copper ions are leaving solution, it leaves an excess of negative charge. So the sodium ions from the salt bridge come down this way to help replenish the positive charge on this side of the cell. Zinc has an oxidation potential of positive 0.76 volts. The copper plus 2 has a reduction potential of positive 0.34 volts, meaning that this entire cell has a total voltage of 1.10 volts. Again, that's assuming that the solutions have a 1 molar concentration. Over time, as more zinc leaves and more copper leaves, the voltage will decrease. As there's less copper to attract electrons and less zinc to release electrons, the voltage will decrease. Eventually, either all the zinc will get used up or all the copper ions will get used up. When that happens, the voltage will reach 0 and the battery will be dead. This is a 6-volt battery that operates on a similar kind of redox reaction. It uses zinc as the anode, but instead of using copper ions as the cathode, manganese ions are used as the cathode. In this case, this outer shell right here is made of zinc. The basic design of the cell is different. This is called a wet cell. I can't imagine taking this and putting it in, like, my cell phone. Because zinc is undergoing oxidation, we call this the anode. The way you can remember this is an ox.
Good Lord, is that an ox?
Because reduction is taking place here, we call this electrode the cathode. And the way to remember that is reduction takes place at the cathode. Red cat. The anode of our voltaic cell is the negative terminal on our cell, and the cathode is the positive terminal. Why is this important? If we don't know what the negative end of our cell is and the positive end of our cell is, if we plug in the device, either nothing's going to happen if we're lucky, or we could blow the entire circuitry of our electronic device. I'm going to reverse the polarity of the wires. I'm going to hook the zinc up to the positive, and then I'm going to hook the copper up to the negative. Look what happens. The needle buries itself in the negative direction because the electrons are not going through the load in the way that the load was designed to be used. This load was designed to measure voltage only if the negative end goes here and the positive end goes here. So we need to make sure that when we plug in our electronic device, that we plug it in with the correct end. When you plug in a AA battery, the bumpy end is positive, the flat end is negative, and the device is designed so that the flat end goes against a spring and then pops into place so that you can't put it in backwards. In these devices, if you do happen to put it in backwards, there's a device called a diode which will prevent electricity from getting to the circuit and blowing out your electronic components. You see, in electronic devices, electrons are designed to flow in only one direction, from negative to positive. And if electrons don't flow in that direction, your device isn't going to work. The electrons come out of the negative anode, through your device, and into the positive cathode. And that's how cells work.